Hello everyone. This is the start of week 11 of our course, and the first lecture today we're going to continue with the hypothesis testing. In fact, this whole week is going to be finishing up with hypothesis testing, so 2 lectures on the topic, and then next week we'll get into the last topic of this course, which is regression. So I hope everybody's hanging in there. We're almost at the end. Just another couple of weeks to go. Okay, so with no further ado, we're going to be looking today at the general hypothesis test on means. And so far we've looked at this general statement, H naught mu x equals mu naught is the null hypothesis, and the alternative, in this particular case, mu x not equal to mu naught, and this is a two-sided test. We're going to test to see if we're far enough away, either the positive or the negative direction to reject H naught and conclude that mu x is not equal to mu naught. And if it's a two-sided test, we're going to be using alpha by 2. So our usual statement is we reject H naught if our test statistic, which is something equals something minus something over something. If that's far enough away in the direction of HA, so the rest of the statement is we reject H naught of our test statistic. This quantity here is something then something, and again it's fill in the blanks. And this first something there's a mistake here, is from HA. That should be HA. And basically HA is in either direction, so it's going to be something like is greater or less than some rejection criterion, depending on whether we choose Z or T, or greater than some rejection criterion. And if it's less than, the rejection region is going to be negative, so the number that goes in here will be a negative value, and if it's greater than here, it's a positive value here. When we do a hypothesis test, we can basically make 2 types of errors, and these are imaginatively enough called type 1 and type 2 errors. Type 1 error is when we reject H naught even though it's true, and the probability of this happening is our selected value of alpha. Okay, so we choose alpha, and basically if we want to avoid this type of error, we should choose alpha to be reasonably small. Type 2 error is a little bit harder to compute, but it's defined as failing to reject H naught even though it is false. And the probability of this is, we call this beta, but this is actually a little bit more difficult to determine, particularly because if H naught is false, then up here we don't know the true mean. We just know that it's not equal to that value, and so we don't have any distribution to judge by. So the probability of type 2 error is difficult to determine, and we're not going to bother working on that in this course. You might find some example questions at the end of this chapter that do ask for the probability of a type 2 error. Just ignore those. We don't cover those. Okay, then the other thing we can do is compute a p-value for each test. As I think we mentioned last day, the p-value is the probability of getting a test statistic at least as extreme as the one already computed in the direction of HA. Okay, so basically up here we have HA is in either direction here. We compute a test statistic here, and depending on what its value is, the p-value is the probability of seeing a test statistic in the future that's at least as far away from the null as this number suggests in either directions. We'll see some examples of those coming up. So let's look at hypothesis tests on the mean. We've already seen a few examples of these in week 10, but they all have the following form. The H naught, the mu x is always taken to be the equality, and we use that mu naught, whatever is on the right hand side there, as the default mean for our test. HA, though, has 3 different forms. Mu x could be less than mu naught. This is a one-sided, and the word here is less than. And here we'll use alpha in our critical region. Then we could have mu x not equal to mu naught, and this is a two-sided test. So our words here are less than or greater than, and our critical region uses alpha over 2. Or we could have mu x greater than mu naught. This is again a one-sided test. The words are greater than, and we use alpha. I should point out that I've revamped the sort of order of this course, and I put all the mean tests together. So that includes both the single sample means and the two sample means, two population mean tests. And so the example numbers are a little bit out of order, but the main thing is that they have a number, so that if I refer back to them, you have to go and find out where it is. Okay, so let's suppose we have this example of structures to rest on piles, and 9 piles are driven at random locations and loaded to failure to basically test their capacities. And we get the following capacities: 92, 86, 104, 100, 98, 102, 88, 95, and 90. And then we ask a series of questions about this sequence of observations. We could ask, what is a point estimate of the individual pile capacity at this site? What is a 95% confidence interval on mean pile capacity? We've done both of these things in previous weeks. And then the final one says, design requirements are that the mean pile capacity is at least 90 kilonewtons. Can you conclude that this requirement is being met at a 5% significance level and report a p-value? This last one, basically, when you see the words "can you conclude," it means you're going to be doing a test. Okay, so we're going to test. We're going to define a null and an alternative hypothesis. If we manage to reject the null, then we conclude that the alternative is correct at that level of confidence. So part A, we need to get, first of all, a point estimate of the mean pile capacity. Oh, yeah, okay, that's the mean. X bar is then just the sum of the observations divided by 9, and that gives me 95 kilonewtons. We'll also need the standard deviation in the next two parts. So S squared is 1 over n minus 1, which in this case is 1 over 8, times the sum of the squared deviations. And if I plug in all these numbers into this, I get 41. So that the sample standard deviation is 6.403. Okay, so this is, it shouldn't be a test there. This is a confidence interval on mu of x with sigma x unknown. Then we'll be using the t-distribution. And for this, we assume that the x's themselves are normally distributed. On the basis of 9 observations, we don't know whether they're really normally distributed, but if they're not, then we can't use the t-distribution, and then we're stuck. We can't do anything else. So we'll assume that they're at least approximately normally distributed so that we can use the t-distribution. So as we recall, our confidence interval has the standard form. LU is equal to something plus or minus something times something, and now it's just a matter of plugging in the quantities into the various somethings. The first something is our estimate of what we're doing the test on. Our test is on mu of x. Our estimate of that is x bar. The second something is either z or t. Since sigma x is unknown, we're going to be using t here. This is a two-sided confidence interval, so it'll be alpha by 2, and then the number of degrees of freedom come from the computation of s squared, which the denominator is n minus 1, so that's the number of degrees of freedom here. And then the last something is the standard deviation of the first something. So the standard deviation of the first something is the standard deviation divided by root n. And this is sample standard deviation in this case because the true standard deviation is unknown. Okay, plugging in the numbers, we had 95 for the point estimate for the x bar. This t is evaluated at, we got 95% confidence, so alpha is 0.05 divided by 2 is 0.025, and the number of degrees of freedom is 9 minus 1, which is 8. 6.403 is our sample standard deviation divided by square root of 9. If we look up in our tables, t of 0.0258 is 2.306. So now I know everything on the right-hand side. Just plug it into my calculator, and I get a confidence interval from 90.08 to 99.92. Okay, and then the last question was design requirements. I think maybe I repeated here, yeah. Design requirements are such that the mean pile capacity is at least 90 kilonewtons. Can you conclude that this requirement is being met at a 5% significance level? As I mentioned before, the words "can you conclude" implies that we're doing a formal hypothesis test. The 5% significance level means that our alpha value is 0.05, and now we have to decide on our hypotheses for our formal test. We want to put what we want to be able to conclude into HA. Okay, so we must have the following format. Basically, we assume the worst, that the pile capacity is less than 9, that we are not satisfying the design requirements. And then basically, if the data supports it, we can reject this and conclude that we are in fact meeting the design requirements. So that we put into HA, that mu of x is greater than 90. Okay, our sentence is we reject H naught if our test statistic, again, something equals something minus something over something. And then we just decide what goes into each for our test. We've seen this in a previous lecture. This one here is either Z or T, depending on whether sigma is known, and this is the test on the mean. So this is a test on the mean, but sigma is not known, so that we're going to put T in here. This something up here is the estimate of whatever the test is on. So the test is on mu of x. Its estimate is x bar. And then this one here is the mean, assuming that the null hypothesis is true. So we always evaluate this null hypothesis at the equality. So mu of x is taken to be equal to 90, and that's what we put in here. And then underneath, we've got the standard deviation of whatever is in here. And so it's the standard deviation of x bar. In this case, the sample standard deviation of x bar, which is s over square root of n. And s, as we had up here, was 6.403. So we plug that in here, 6.403 divided by square root of n. And we get, in the end, plus 2.343 is our value of t. And that means that basically we're approximately maybe a little bit more than 2 standard deviations away from where we should be in the positive direction if the null hypothesis is true. I think I mentioned in one of my earlier lectures that this meant we are 2.3 standard deviations away from where we should be. That's not quite true because the t distribution has a wider distribution and its standard deviation isn't quite equal to 1. It's a little bit bigger than 1. But it'll be approximately something like 2. What's it going to be? This is 2.3, so something like 2.2, 2.1 standard deviations away from the null hypothesis. Okay, let's continue our sentence. We reject H naught if our test statistic t equals 2.343 is something than something. And now we fill in the numbers here. This first something comes from HA, so we look up here and see what this thing is. And it's the greater than sign, so we put greater in here. Since this is in the positive direction, the sign here is plus, and our test statistic, our critical region is T, evaluated at alpha with n minus 1 degrees of freedom. Alpha because this is a one-sided test. If it had been two-sided, it'd be alpha by 2. Alpha in this case is 0.05, n minus 1 is 8, and if we look up in our tables, that's 1.860. We see that 2.343 is bigger than 1.860, so we say which it is. So this sentence is true. So we can reject H naught and conclude with at least 95% confidence that mu of x is greater than 90 kilometers and that the design requirements are being met. Okay, so that's, so the other thing we asked for was the p-value. For the p-value, we look back up at our test statistic. We got t is equal to 2.343, and the p-value is the probability that if I were to repeat this experiment again, what is the probability that I see a test statistic at least as big as this in the direction of HA, so in the positive direction. So my p-value is the probability that at t with 8 degrees of freedom is greater than 3.343. And to get this, we need to look at our summary pages. If you take a look in there on the 8th line, you'll see the probability that t is bigger than 2.306 is 0.025. and the probability that t is greater than 2.896 is 0.01. And these two numbers are on either side of this. Actually, this one is very close to this one. So I would say this probability is very close to this one, but somewhere between this one and this one. So if I look at this, this one here is going down, so I would suggest that probably the t is greater than 2.343 is about equal to 0.02. And this is a reasonably small p-value. It shows reasonably strong support for the alternative, HA. Basically, we reject H0 anytime we choose an alpha value which is bigger than this p-value. And we chose alpha equal to 0.05, and it's greater than the p-value, so that means we should reject, which is what we concluded up here. Okay, so maybe we'll do another example. We're going to test the hypothesis that the average content of containers of a particular lubricant is 10 liters if the content of a random sample of 10 containers are given as follows. So there's 10 observations here. We're going to use a significance level of 0.01. This means that our alpha is equal to 0.01. And assume that the distribution of contents is normal. We have to assume this because we don't know the true standard deviation. We're going to use the t-distribution. Okay, so to do this, we first of all need to compute sample mean and sample standard deviation. We can do this before we've set up the hypothesis test itself because we're going to need these quantities later on. So basically, if I add up these numbers here and divide by 10, I get the x bar value is 10.06 liters. And if I take these numbers, subtract that sample or x bar sample average and square them, add them up and divide by n minus 1, I get a sample variance of 0.06044. And I take the square root of that, I find that the sample standard deviation is 0.2459. Okay, so now we need to decide on the test. To do this, we have to look back up here. And it says, test the hypothesis that the average content of containers of a particular lubricant is 10 liters. It doesn't ask here whether it's greater than or less than, just is it 10 liters. So I would suggest that this is going to be a two-sided test. And that's the way I've taken it. So my H0 is that the mean is 10 liters as is suggested by the sentence up here as the null hypothesis. And then our alternative is that it's not equal to 10 liters. And then basically, we're going to, if we can reject H0, then we can conclude that the mean content, the average should be the word mean here, is not 10 liters. Okay, so basically this is a two-sided test. That means we're going to be using alpha by 2 since we don't know the standard deviation. The test statistic and the critical region will be t. Alpha is 0.01. Divide that by 2, I get 0.005 with 9 degrees of freedom, 10 minus 1. And if I look that up in the table, I get 3.250. So our sentence is, we reject H0 of our test statistic. Since sigma x is unknown, our test statistic will be t is equal to something minus something over something. The first something is the estimate of whatever the test is on. Test is on mu of x, so this is x bar. The second something is the mean according to the null of the x bar, and so that's going to be this 10. So 10 goes in here, and underneath we have the sample standard deviation of the x bar in the value that's in here. And that sample standard deviation is s of x divided by square root of n. Okay, so we know everything on the right hand side. We plug in the numbers. We get t is equal to 0.772. Okay, so the sentence now is we reject H0 of our test statistic. T equals 0.772 is something then something. Well, we have to look at HA for what words we use here. This is not equal to, so it's the words are either less than minus T alpha by 2 with n minus degrees of freedom, or greater than plus T alpha by 2 n minus 1 degrees of freedom. So this is either less than minus 3.250 or greater than plus 3.250, which it isn't. 0.772 lies between these two bounds. So we cannot conclude with 99% confidence that mu of x is not equal to 10 liters, mu of x might equal 10 liters. In fact, we can see from our estimate here, 10.06, that's pretty close to 10 liters. So it suggests that the filling process here is actually quite accurate. A p-value, we're looking for the probability that if we repeated this test, we would exceed the test statistic computed in the direction of HA. In this case, the direction of HA is either negative, less than, or positive, greater than, since we have a not equal sign. So our p-value is the probability that t with 9 degrees of freedom is either less than minus 0.772, and that's our test statistic up here, or greater than 0.772. And so this is a sort of a thing you have to watch out for with the two-sided tests. This distance here is taken to be an absolute distance from h naught in either direction. So it's probably that we're less than minus that value or greater than plus that value. Well, this t distribution is symmetric, so this is just twice the probability that t9 is greater than 0.772. And for this, we have to look in the t distribution table. We see that the probability that on the 9th line, the probability that t is greater than 0.703, which is less than this thing, is 0.25. And the probability that it's greater than 1.383, which is bigger than this thing, is 0.10. It's going to be closer to this one because 0.772 is pretty close to 0.703. So I would guesstimate that the probability that T9 is greater than 0.772 is around 0.22. So pretty close to this, but a little bit more in the direction of this one. So I would, the p-value then is going to be twice this probability here, which is 0.44, which is a pretty high p-value, and basically it gives strong support for h naught in this case. And again, we could see that because our x bar was really quite close to h naught. We selected an alpha value of, what did we choose up here? 0.01, so we chose a very small alpha value, but in any case, we could choose a much larger alpha value and still not be able to reject h naught. But since the alpha value is less than the p-value, we cannot reject h naught. It may be true. Okay. Okay, then that's probably enough for single sample tests on the mean. Let's take a look at tests on the differences in means. Now we saw this differences in means in confidence intervals, and we saw then that we had 3 cases to consider. And we'll have exactly the same 3 cases here for hypothesis tests. One of the cases is where the sigmas are known. And this basically just boils down to our test statistic being z now, and our standard deviation of x bar 1 minus x bar 2 is just the square root of the variance of x bar 1 plus the variance of x bar 2, which is variance of x divided by n1, variance of x1 divided by n1 plus the variance of x2 divided by n2. The second case is where the sigmas are unknown, and we assume that they're equal and pool the data. Okay, so we're going to do the same thing now with the hypothesis test. And then the third case for the differences in means is when the data is paired. And for that, we saw for the confidence intervals that we compute the differences, x1i minus x2i, and from that get a d bar and a SD, and then treat this as basically a single sample except in terms of d instead of in terms of x. Case 1, where the sigmas are known, if we consider the test mu x1 equals mu x2 versus mu x1 not equal to mu x2, so this is a two-sided test. What we're really testing is mu x1 minus mu x2 equals 0. So this basically, this 0 gives me the mean of this difference. And then the alternative is that this difference is not equal to 0. And as I mentioned, that's a two-sided test. Our sentences, as usual, reject h naught over test statistic. Something equals something minus something over something. If we know the sigmas, and this is the test on the means, we put z in the first something here, so that's our test statistic. The something up here is the estimate of the test, which is mu x1 minus mu x2, and that's x bar 1 minus x bar 2. And then in here we put the mean according to the null, so the mean of mu x1 minus mu x2 is assumed to be 0. So 0 goes in here. And underneath here, we put standard deviation of x bar 1 minus x bar 2. And we've seen all of this stuff already. The 0 just disappears. We get x bar 1 minus x bar 2 over the square root of sigma x1 squared over n1 plus sigma x2 squared over n2. And basically, we reject h naught of our test statistic. Whatever we compute here is either less than minus z alpha by 2. So alpha by 2 appearing here because we have a two-sided test, or greater than plus z alpha by 2. Okay, so don't forget the signs. And anytime you've got less than here, the sign here is negative, and you get greater than here, the sign here is positive. Let's, for example, just suppose that we got a test statistic of minus 2.4 up here. What would our p-value be? Well, basically, this 2.4, this is a two-sided test, as mentioned. So this 2.4 is deemed to be a distance away from the null in either direction when we go to compute the p-value. So it's the probability that we exceed 2.4 either in the negative direction or in the positive direction. So I've just basically said this here. So p-value is the probability that z is less than minus 2.4 or greater than plus 2.4. This is symmetric, so we know that this is just 2 times the probability that z is greater than 2.4, and the probability that z is greater than 2.4 is 1 minus phi of 2.4. And then, so I just look it up at the table what the phi of 2.4 is, to 1 minus that, and multiply the whole thing by 2. Okay, case 2, where sigma x and sigma x, sigma x1 and sigma x2 are unknown, but we're going to assume them to be equal. In this case, we pool the data and compute the pooled sample variance, which is a weighted average of the two individual variances sx1 squared and sx2 squared. Don't forget to put the squares on these. And our number of degrees of freedom here is going to be n1 minus, plus n2 minus 2. We lose 2 because we have, in this case, we're going to have two estimators, x bar 1 and x bar 2. To illustrate this, let's look at an example. Let's suppose a mining company buys its roof supports from company 1. Company 2 has sent them a brochure claiming that the roof supports have increased ductility for only slightly more cost. Ductility is the area under the stress strain curve, which is basically the amount of energy absorbed during failure of the roof supports. Increased ductility is good because it provides warning prior to failure, so it's not a brittle failure. So let's suppose we take 50 samples from each company and test them to compare their products. Sample means and standard deviations are x bar 1 is 562, x bar 2 is 583, so it looks already like the second company, its claim is correct that they are having increased ductility, but this may be just due to random sampling error. With standard deviations, sample standard deviations 12 and 8. Should the company seriously consider buying from company 2? Set up the problems and consider the consequence of the two types of errors. Well, okay, so first of all, let's decide on what hypothesis tests we want to test. And I would say that I'm going to assume by default that the old supports are better. These are what we've been using currently. We know that they're safe or acceptably safe. So I'm going to assume by default that they're better, so that if I reject this, then I know that the data is saying that the new supports are in fact better. So basically, I'm writing it this way. The mean of x2 is less than the mean of x1, so that means the supports from company 2 are worse than the supports from company 1. And then the alternative is that the mean from x2 is bigger than the mean from x1, so that these supports are then proven to be better at that level of confidence. So they will then consider buying from company 2 if the new supports are proven to be better. These things here, we're going to actually test we're going to write it this way. H naught is mu x1 minus mu x2 equals 0, so we'll take it at the equality. That gives us a distribution to use. And then the alternative is that mu x1 minus mu x2 is less than 0. That means that mu x2 is less than mu x1. No, sorry, I take that back. Mu x2 is greater than mu x1. And this is a one-sided test. Our types of errors are as follows. Type 1 error, if you remember, is when we reject H naught even though it is true. If we reject H naught even though it's true, then we're going to consider switching to company 2 even though their supports are no better. This means we're gonna pay more money, plus it's less safe. So we want to avoid this. A type 2 error is where we fail to reject H naught even though it is false. So we fail to reject H naught. We're not going to consider buying from company 2 then, even though they really are better. We are missing out on a safer product, although we are saving some money. So we actually want to avoid this as well. We would prefer not to miss out on a safer product. So both of these errors are of value to avoid. So basically we want to choose alpha to be small but not too small. Alpha small reduces the probability of a type 1 error, but the smaller alpha gets, the bigger the probability of a type 2 error. So we don't want to choose alpha to be too small. So let's try alpha equal to somewhere reasonable value that we usually choose 5%, and we'll report also a p-value in this test. Okay, so in this problem, sigma x1 and sigma x2 are known, so we're assuming them to be equal and we're going to pool the data. So that means we compute this pooled sample variance is the weighted average of Sx1 squared and Sx2 squared, weighted by the number of observations from population 1 and number of observations for population 2. So we'll plug in the numbers. We had 50 observations from each, so I got 49 times 12 squared plus 49 times 8 squared, divided by 100 samples altogether minus 2, which is 98, and I got 104 for the sample variance, pooled sample variance, which is the improved estimator of this unknown variance. And so our sample standard deviation is the square root of this, which is 10.2. Okay, that means then plugging in the numbers and looking back at what we had for the sample standard deviation of x bar 1 minus x bar 2 is SP times the square root of 1 over n1 plus 1 over n2. Again, plug in the numbers. We got 10.2 square root of 2, 1 over 50 plus 1 over 50 is 2 over 50, and that gives me 2.04. We had for this problem, we decided we're going to use 0.05, so our critical value is T alpha with N1 plus N2 minus 2 degrees of freedom. Alpha is 0.05, N1 plus N2 minus 2 is 98. There isn't a 98 in the T table, so this is pretty close to 100, so I'm just using T of 0.05 out of 100, and this is 1.660. So our sentence is we reject H naught if our test statistic. In here I put T because our sigmas are unknown. Here's our estimator of mu x1 minus mu x2, which is x bar 1 minus x bar 2. Here is the difference according to H naught, the mean difference according to H naught, which was 0. So I'm going to put 0 in there. And underneath here I get the sample standard deviation of this difference, x bar 1 minus x bar 2. And I know all of these numbers now. Our x bar 1 was 562, x bar 2 is 583. The mean according to the null is 0. And underneath here, we computed up here that this sample standard deviation is 2.04. And I get T is minus 10.3. This is a long way away from H naught. It's minus approximately 10 standard deviations away from what H naught is claiming. Okay, so our sentence is we reject H naught if our test statistic T equals minus 10.3 is, and here I want to put the direction of my alternative, which is this thing here, and the word is less than. Words are is less than, and my critical region is then minus T alpha with N1 plus N2 minus 2 degrees of freedom, which we computed it's up here is minus 1.660, which it is. Minus 10.3 is way less than minus 1.660, so we conclude with at least 95% confidence that mu x2 is bigger than mu x1 and consider buying from company 2. The p-value is the probability that T98 with 98 degrees of freedom is in this case we're looking in the direction of HA, which is less than the test statistic that we computed of minus 10.3. Because this is so large, I approximated this with Z. So this is approximately equal to the probability that Z is less than minus 10.3. And if I plug that into my computer program that computes phi of Z values for me, I see that this is a very, very small probability of 4 times 10 to the minus 23. So this shows very, very strong support for HA. Okay, so that mu x1 is bigger than mu x2. And basically, recall that we reject H naught whenever we select an alpha value that's greater than the p-value, and we would always select an alpha value that's bigger than this. Okay, and then the third case is when we have paired data. Recall that when data are paired, there's something in common between the pairs that make them highly correlated. When this is so, we have to take the differences to eliminate the effect of that correlation. So we define di is the difference between x1i minus x2i. Evaluate these for all of the pairs, and then compute d bar as the average and s squared of d as the sample variance of the d's. Let's illustrate this with an example. So a new technique for impregnating the surface of steel with carbon to harden it is under investigation. The new technique is to be adopted if it does not result in a less hard steel surface. 10 short sample plates are treated, half of the plate with the existing hardening method, the other half with the new method. And this is the sentence that you want to pay attention to. It basically says we're going to take a plate and divide it in half. We're going to treat half of it with the old method and half with the new method. That means if the plate starts off being weak or soft, it'll be softer in both of them. So there's something in common between our observations. So basically we're saying that whenever we see lower values here, maybe this is the lower value here, they tend to both be lower. And then whenever we see higher values, where's the highest? Here. Well, maybe it's not so obvious, but here, there we go. They tend to be both higher. In any case, there is something in common with these pairs of measurements, so I would consider them to be paired measurements. And that means that I'm going to compute the differences. So I take the old, which I'm going to call this population 1, subtract the new, which I'm going to call population 2. 68 minus 65 is 3. 66 minus 69 is minus 3, and so on and so forth. So we build up all the d values. And then the question is, should the new method be adopted? So basically we're going to want to check to see if the new method does not result in a less hard steel surface, and we'll have to decide how to set the test in a few minutes. We're going to test at a 5% significance level, which means we'll take alpha to be 0.05, and we'll report a p-value. Okay, so as I mentioned, since the same piece of metal is being used for both treatments, there's something in common, and so this is paired data. And we want to compute the DIs, and usually what I do is just add another line to the table and put the DI values in there, and then compute D bar as the sum of these numbers divided by 10, which gives me 1.5. And the sample standard deviation is the sum of the squared deviations between these numbers and 1.5 divided by n minus 1, which is 9, and that gives me 4.06. Okay, so our default position, let's go look up this again. Okay, so the new technique is to be adopted if it does not result in a less hard steel surface. So I think I read this as meaning the new technique is going to be adopted by default, but not if it's shown that it results in a less hard steel surface. So basically, if mu d is mu x1 minus mu x2, and mu x2 is less than mu x1, then this thing is going to be positive. Okay, so I'm going to set my tests up as follows. The null hypothesis is that mu x2 is bigger than mu x1 by default, so that this quantity here is less than or equal to 0. We always put the equality here, and we use the equality in the test, against the alternative where the difference mean of d is greater than 0, which would mean that mu x2 is less than mu x1, and so we don't use the new method. Okay, our sentence is, we reject H naught of our test statistic, something equals something minus something over something, and then just plug in the numbers. We don't know the true standard deviation, so this is t over here. This is the estimate of whatever our test is on. Our test is on the mean of D, so this is D bar. This is the mean of D according to the null, which is 0. And remember, we use the equality here. So we stick 0 in there, and underneath we got the sample standard deviation of D bar, which is 4.06 divided by root n. So now we know everything we know, and we could compute T equals 1.168. Okay, so we continue our sentence. We reject H naught of our test statistic. T equals 1.16668 is, and then this word here comes from HA. This is the greater than symbol, so we put greater than, and because we're looking in the positive direction, there's a plus sign here. Our critical region is T, subscript alpha, so because it's a one-sided test, we use alpha here, not alpha by 2. And with n minus 1 degrees of freedom, plug in the numbers. Alpha is 0.05, 10 minus 1 is 9, and look in our tables, this is 1.83. This 1.168 is not greater than 1.83, so we fail to reject H naught. The new method may be better, so we'd adopt it. Okay. P-value is going to be the probability that if I were to repeat this, my test statistic would be at least as big as the one I computed, 1.168, in the direction of HA. HA is in the positive direction, it's greater than here, so it's probably the T9 is greater than 1.168, and if we look at it in our t-tables, this is approximately equal to 0.17. And the 0.17 is not particularly small, so it should suggest moderate support for the null hypothesis. We could only reject it if we chose an alpha value which is bigger than 0.17, so we could only reject it with 83% confidence or lower. And that concludes the hypothesis tests on the means. Our next lecture will look at hypothesis tests on proportions and on the variance. Thank you. See you in a bit.